Good morning, Ramesh Babu. Ramesh Babu, good morning. Vijay Kumar, good morning.
Good morning, sir. Good morning, sir.
Slide కనపడుతుందమ్మా?
కనపడుతుంది సార్.
Okay, restart.
Yes, sir.
So yesterday we have discussed this last part of the unit, testing of hypothesis. So hypothesis means it is an assumption made about parameter or probability function which may or may not be accepted or rejected at certain level of significance is called hypothesis. Simply you can say that hypothesis is a statement we made relating to the given problem. So the average height of soldiers in the army is 165 centimeters. So this is a statement relating to a soldiers population. So it is a hypothesis. The given drug was the causes cures. The given drug cures 80% of the patient taking it. So that is also a statement. So it is also called hypothesis. So based on some procedure, we will come to the conclusion whether we accept or reject these statements. So that is a procedure based on the procedure. So now, and already I told you that hypothesis is of mainly two types: null hypothesis H naught and alternative hypothesis is H1. So hypothesis in which we assume that the difference between estimate and parameter is zero, in which usually a hypothesis of no difference is denoted by H naught, and it is called null hypothesis. So null hypothesis is a hypothesis in which we assume that the difference between the estimate and parameter is zero. So, and is also usually a hypothesis of no difference. You can also call it as. So, and it is denoted by H naught. And alternative hypothesis is a hypothesis in which is opposite to of H naught. Suppose H naught you take X naught is equal to mu, then H1 is equal to X bar is not equal to mu. When H naught is not equal to mu, H1 is not equal to mu naught, H1 mu is not equal to mu naught, okay? Then mu greater than mu naught or mu less than mu naught. So H1 mu greater than mu naught or less than mu greater than mu naught, you can say that is a right tail test. Mu less than mu naught is called left tail test. So these two tests are called single tail tests. We'll discuss now. Then simple hypothesis. A hypothesis which specifies a distribution completely or its parameters completely, known as a simple hypothesis. For example, here the distribution is normal with f of x is 1 by 3 into 2 pi square root e power minus half x minus 7 by 3 whole square, where here mu and sigma are known. So that means parameters are known completely. Therefore, it is a simple hypothesis. And in second example, lambda is equal to 4. The lambda is the parameter for Poisson distribution and it is given. So complete information is known relating to the distribution. So it is another example of a simple hypothesis. Similarly, composite hypothesis means one which specifies some parameters only. Partial information is given. Then that hypothesis is called composite hypothesis. Suppose here H naught mu is equal to 7 and sigma is not given. Then it is called composite hypothesis. Next, like that. Next, test statistic. So it is a statistical procedure by which we can decide whether there is any difference between a statistic value and the parameter value, difference between two statistic values, and any effect of treatment on the given variables, etc., based on the probability. So various tests of significance will be divided into two parts: large sample test of significance, which you have to study in this unit, and a small sample test of significance when n less than or equal to 30. Here it is n greater than 30. So when n greater than 30, you use J test. When n less than or equal to 30, you use F test, T test, or chi-square test. This is come under next unit. This part to come under next unit, and this part you have to study here only now. Now errors in sampling. When you're doing sampling, definitely there may be a cause the chance of making errors. That these errors are two types: type 1 error and type 2 error. These are very important. Type 1 error means if you reject H0, null hypothesis H0, when it is true is called type 1 error, and it is also equal to alpha. Probability of rejecting H0, H0 is true, is equal to alpha. This is type 1 error. Type 2 error means we accept the hypothesis when it should be rejected. We accept the null hypothesis when it should be rejected. We say that a type 2 error has been made. So this can be written as probability of accept H0 when it is true or when it is false. This is beta. So this can be written in dichotomous table. This is called dichotomous table. Reject H0 when H0 is true. Type 1 reject H0 when H0 is true. Type 1 error. Reject H0 when H0 is wrong is correct decision. Accept H0 when H0 is true, correct decision. Accept H0 when H0 is wrong is a wrong decision. That is type 2 error. So this is the general example which you are giving always. If a doctor rejects to treat a treatment who is really a patient with some disease, then doctor commits type 1 error. On the other hand, if the doctor gives treatment to a healthy person, there also he committed some mistake that is called type 2 error. So best you write these examples and type 1. So this type 1 error, null hypothesis, alternate hypothesis, type 1 error, type 2 error, these are very, very important for short notes. So next, level of significance. So is nothing but type 1 error. Probability of rejecting null hypothesis when it is true is called level of significance. When it is true, that is equal to alpha, type 1 error. So type 1 error is called LYS, level of significance. If you adopt 5% LYS, implies that whatever you assume in the statement, if you repeat that experiment 100 times, 95 times it is true, as you said as you assume in the assumption, and only 5% there may be any deviation. Similarly, 1% means 99% of times, 99 trials, if you do, or if you conduct, then whatever you assume in the assumption hypothesis, 99 times it will be use same result, and there is only 1% of deviation. That is the meaning of that. Generally, alpha will be taken as 5% or 1%. Next, degrees of freedom. The number of degrees of freedom nu in general is total number of observations minus the number of independent constraints imposed on the observations. For example, in case of chi-square distribution, degrees of freedom is equal to n minus k, k is equal to 1. Because of the assumption constraint is sigma y is equal to sigma ei. So this is another thing. In case of R into contingency table, S into T contingency table, degrees of freedom is S minus 1 into T minus 1. So this is another important thing. So level of significance is also important for examination point of view. You learn these degrees of freedom also. Next, critical region. Generally, for test of significance, the sample space S may be divided into two regions, say omega and S minus omega. If any point X falls into this omega, then we reject the hypothesis, reject H0. Otherwise, any point falls in S minus omega, we accept H0. Then the region of rejection, omega, this region of rejection, this is the region of exception. This region of rejection is called, critical region. Is called critical region, and the region of acceptance S minus omega is called as acceptance region. So the sample space is divided into two parts: omega, that is critical region, and S minus omega, that is acceptance region. If any point fall in this omega, we'll reject H0. If any point fall in this omega, S minus omega, will accept H0. So like that. So probability of type 1 error, the same thing we are written here. X belongs to omega and H0 is true. Reject H0. When X falls in omega, we'll rejecting H0. So probability of rejecting H0 when H0 is true is alpha. So type 1 error. Now accepting H0 when H0 is false, beta. So this is type 2 error. So alpha is known as size of the critical region. Beta is known as the size of the acceptance region. Alpha is known as size of the critical region, and beta is known as the size of the acceptance region. So now we'll come to this one-tailed and two-tailed test. One-tailed test of any statistical hypothesis where the alternative hypothesis H1 is expressed by the symbol less than or the symbol greater than is called one-tailed test. Yes, if there are two types of hypothesis, H0 and H1. In case of H1, you write symbol like this: H1 mu is less than mu1 say. Then or the symbol H1 mu greater than mu1 say. Then these type of symbol, expressions are called one-tailed test: less than or greater than. Since the entire critical region lies in one tail of the distribution of the test statistic. In case of single tail test, the critical region will be either this side when this is n z greater than mu naught. Okay, mu greater than mu naught, then entire critical region alpha lies in right tail, right tail. If suppose h1 mu is less than mu naught, then it is called left tail. The entire critical region lies on the left of this. So here it is negative probability minus z alpha you have written. So in case of one tail test, alternative if the alternative h1 hypothesis is alternative hypothesis is h1 mu less than mu1 or h1 mu greater than mu1, then these two, then we say that they are called single tail test or one tail test. Suppose the critical region is mu greater than mu naught, then we have right tail test like this. Mu greater than mu naught means right tail test. This is called right tail test. So here the critical region lies, region of rejection or critical region both are same, lies on the right side of the tail. Suppose h1 mu less than mu naught, then the critical region lies on the left tail of the curve, probability curve, that is minus z alpha. So that is called, so this is a left tail test, here right tail test. Both tests are called single tail test. So that is the meaning. So once again I'm telling, when h naught is mu is equal to mu naught, then if you take h1 mu greater than mu naught, the curve will be like this. Here the region of the alpha, the region of rejection or critical region lies on right side of the right tail of the curve. So the remaining part is called acceptance region. This is a rejection region. From here to end, it is called acceptance region. That is called 1 minus alpha. Similarly, if h naught, h1 mu less than mu naught and h naught mu is equal to mu naught, h naught mu is equal to mu naught and h1 mu less than mu naught, then the critical region will be left tail on the left side of the tail. So left tail. So here minus z alpha, we have to take this. So these two come together, join together, called as single tail test. So if you observe in h1 greater than or the symbol less than, we can say that they are single tail tests. So next, if suppose h1 is not equal, is appears h0 h1 mu is not equal to mu naught, then it is called two tail test. Two tail test, where the critical region is split up into two equal parts, one in each tail of the distribution of the test statistic. So here suppose I write h1 mu is not equal to mu naught. So this is two tail test. So symbol mu not equal there in between them, then you say that it is a two tail test. In case of two tail test, this critical region alpha is divided into alpha by 2 and alpha by 2. So this is alpha by 2, this is alpha by 2. If I add both, alpha you will get, that is critical region. So in case of two tail test, alpha by 2 will be, alpha is split into alpha by 2 and alpha by 2 on the both the left and right tails of the curve. So the remaining is called acceptance region. So I think now here it is clear. So in case of h1 mu greater than mu naught, we will have right tail test, right tail test. In case of h1 mu less than mu naught, we can give left tail test. In case of h1 mu is not equal to mu naught, we have two tail test. So in case of two tail test, this alpha is split into two parts. So alpha by 2 here, alpha by 2 here. I think now we are clear about that. So these two are called single tail test. These two are called. This is a right tail test. This is a left tail test. Both of them are called as a single tail test. And it is since the critical region is split into two parts, alpha by 2 and alpha by 2, then it is called as a two tail test. So that is now by comparison of critical values and calculated values, we reject or accept the null hypothesis at 5% or 1% as follows. So first, by using test statistic either Z, if Z calculated value is how Z, if you calculated Z value, that is called Z calculated value, then you have to use this. For two-tailed test, mod of Z calculated value is greater than critical or table value at 5% LOS, reject H0. If calculated Z value is greater than table value at 5%, we reject H0. If mod of calculated value is less than table value, we accept H0. So based on these two sentences, we will come to the conclusion whether we have to accept or reject the given hypothesis, whatever you assumed in the hypothesis. So if calculated, in case of two-tailed, we take modulus. We take modulus. In case of two-tailed, we take modulus because it is minus Z alpha and Z alpha is there. So we take mod Z. So in case of two-tailed test, we will take modulus. If calculated Z value is greater than table value or 5% LOS, we reject H0. If calculated Z value is less than table value or 5% LOS, then accept H0. So these are the 2 points to be remembered. So next, at the same time, right tail test. Same, it is whatever you are assuming in the two-tailed, right tail also same. If the calculated Z, but no need of taking modulus here, right tail test, because it is on the right side, so it is always positive. So if calculated Z is greater than table Z value at 5% or 1% LOS, we reject H0. If calculated Z value is less than table value at 5% or 1% LOS, we accept H0. So here also, if calculated Z value, mod calculated Z value less than table value, accept H0. Here also, without mod, Z less than calculated value is accept H0. So here, both are the same. In case of two-tailed test and right-tailed test, these two sentences are same. Only modulus you have to take in case of two-tailed. If the calculated Z value will get negative, then you take modulus so that it becomes positive. So here always getting positive values, that's the right tail test. And left, it is opposite of these two. If calculated Z value is less than table Z value at 5% or 1%, reject H0. And calculated Z value is greater than table or critical Z value at 5% or 1%, accept H0. Whereas these two are opposite to of these two. Here it is a calculated Z value is greater than critical value, we accept H0, sorry, we reject H0. Here, if calculated Z value is greater than table value, then we accept H0. Here rejecting, here accepting. Similarly, here accepting, here rejecting. So opposite to the top. This is only in case of left tail test. So now, what I say that in case of two tail test, right tail test, these are same. Whatever you're assuming, these are same. And in case of right tail test, this is opposite to this of left tail test, which is opposite of right tail test. If calculated Z value is greater than critical value, we reject. Whereas here, if calculated Z value is greater than critical value, we accept H0. Here, if calculated Z value is less than critical value, we accept. Whereas here, we reject. So you have to identify this difference. So this is the conclusion how to draw the decision making based on these points. We will see in later in while solving the problem. Two-tailed test. If you are testing a hypothesis at 5% LOS, the size of the acceptance region on both sides of the mean of 0.475 and size of the rejection is 0.25. So this area from here to here, it is this is 0.5, and if alpha is 5%, you divide this alpha 5% means 0.05, and it is divided into two parts, we will get 0.025. So we will take 0.025 here and other 0.052 here. If it is 0.025, the remaining area here it is 0.475. And similarly here also the remaining area is 0.475. This is 0.025. So by taking this 0 to Z alpha is equal to 0.475. By reverse tracking, we'll get Z value is 1.96. By taking this area, Z is equal to 0 to Z alpha say is equal to 0.475. By reverse tracking from the normal tables, we can have the idea of Z alpha value as 1.96. This is the way of getting Z alpha by 2 value is 1.96 means this is the way of right. So this is Z alpha by 2. Suppose in the same way, hypothesis is at 1%, then alpha is 0.01, alpha by 2 is 0.005, and other 0.005 is here. So if you add these two, you will get a 0.01. So the remaining, this is 0.495, this is 0.495. So by taking 0 to Z alpha is equal to 0.495 by reverse tracking, we will get a Z is equal to Z alpha is equal to 2.258. So this is a way of getting that Z alpha value, Z alpha by 2 here, Z alpha by 2 here value 2.258, 2.58 will get like this. So from this, in case of two-tailed test, the alpha is 5%, Z alpha by 2 is 1.96, and alpha is 1%, Z alpha by 2 is 2.58. This you have to remember. This is the way of getting a table value, Z alpha value, Z alpha by 2 value, like this here, Z alpha by 2 value. If it is a single tail, then you take it as Z alpha, because it is a two tail means here it is Z alpha by 2. You correct this Z alpha by 2. Here also Z alpha minus Z alpha by 2. This is plus Z alpha by 2. So this is plus Z alpha by 2. This is minus Z alpha by 2. So that's why I have taken minus 2.58, here 2.58. So this is the way of finding the table values for when alpha is 5% and alpha is 1%. So when alpha is 5%, Z alpha by 2 is 0.5 divided by 2, 0.025. So here this is 0.025. So Z alpha by 2, you see here, Z alpha by 2 is 0.025. So if it is 0.05, the other 0.025 is taken here. So you take this, this is 0.5. If it is 0.025, the remaining area is 0.04575. So here you take the area from 0 to Z alpha by 2. So integral 0 to Z alpha by 2 phi z dz is equal to 0.475. By reverse tracking, we will get 1.96. So the same thing here, we will take minus 1.6 because this is also same. Here 4 points 0.475 and here also 0.025. So we will put the same answer minus 1.96. In the same way here also, when alpha is 1%, Z alpha by 2 is 0.01 by 2 is equal to 0.005. So if it is 0.005, here also 0.005. The remaining area is 0.495. So take Z is equal to 0 to minus Z alpha by 2. YZ dz is 0.495. Reverse tracking, we will get Z alpha by 2 is equal to 2.58. So same thing with the, we will take minus on the negative part. Similarly, example, alpha is 5%, 0.05. So we'll get like this. This is the same test, single tail test. Single tail test means, yes, when alpha is 5%, this is Z alpha, because alpha is entire, it is a right tail test, entire here 0.05. If it is 0.05, the remaining part here it is 0.45. So then you can find out Z alpha is equal to integral 0 to Z alpha phi z dz is 0.45, and reverse tracking will get the value. And similarly, left tail test, the entire critical region lies on the left tail. Here the entire critical region lies in the right tail. So this is left tail, this is right tail. Here alpha is taken as it is. Suppose alpha is 5%, 0.05 is taken here. Here also 0.05 is taken. Alpha is 1%, 0.01 is taken here. And that alpha is not split into alpha by 2 and alpha by 2 because it is single tail. This is right tail, this is left tail. We will take alpha as it is. So whereas here alpha is divided, because it is a two tail, alpha is divided into two parts and sharing on both sides, equal shares, 0.05, 0.05, like that. So these two are the cases of right tail and left tail, single tail, single tail. Okay. So here values are given. So in case of two-tailed, at 1%, Z alpha by 2 is 2.58, 5% 1.96, 2% 2.3. You have to remember this table. 10% Z alpha by 2 1.645. So here when alpha is 1%, 5%, 2%, 10% are given. Generally we use 2%, 5%, 1%. Similarly, when right tailed, it is Z alpha 2.33, Z alpha is 1.645 at 5%, and at 2% 2.06, Z alpha value at 10% is 1.28. Left tail means you have to take minus because it is in the left tail. Left part is negative. So minus Z alpha is minus 2.33, minus Z alpha is minus 1.645. Here also minus 2.06. Here also minus 2 Z alpha. Minus Z alpha is minus 1.28. So like this, these are the table values we will get from normal tables, and it is tabulated here to remember. So you please remember this table. 1%, 5%, 2%. These are very important, usually asked. So next, procedure of testing a hypothesis. H naught. Procedure of testing a hypothesis. Step 1. Set up the null hypothesis. For the given problem, you write H naught, some statement. Suppose two parameters you are asked to test. You are asked to test the estimate and parameter. Suppose you are asked to test the difference between x bar and mu. Then you set up the H naught. H naught x bar is equal to mu. X bar is equal to mu. That means there is no difference between sample mean and population mean. So like that, first you set up the null hypothesis. Next, in second step is alternate hypothesis, which will be opposite to this. So this will enable us to decide whether we have to assign single tail test or that is a right tail test or left tail test or two tail test. Okay, suppose you take here h1 x bar greater than mu, let us say h1 x bar greater than mu, you take right tail test. Suppose h1 x bar, h1 dot x bar less than mu, then you take left tail test. So suppose h1 colon x bar not equal to mu, not equal to mu, then you can say that two tail test. So whether you have to take right tail or left tail or two tail based on this h1. This is second step is important. First you have to write set up the h1 h0, and in second step you have to write based on the given problem. You can write it as whether it is left tail or right tail or two tail. So this is second step. Third step, you have to choose level of significance. If you ask it particularly find at 5% or 1%, then you have to follow. Otherwise, you generally will take 5% or 1%. Choose the appropriate LOS depending on the reliability of the estimates. This is to be decided before sample is drawn. That is, alpha is fixed in advance. So this is some simple thing. So you generally will take alpha is 5% or 1%. Okay. So next, test statistic. So if n greater than 30, we use Z test. If n less than 30, we use t test or f test or chi-square test. Here we are discussing only n greater than 30. That means large samples only. So we'll check Z is equal to t minus, t means statistic, t minus expectation of t divided by standard of t. This is standard formula. T minus expectation of t divided by standard of t under the h naught. X bar is equal to mu, let us say. So next conclusion. If you have to follow that sentences. If h naught is if h1, whatever you chosen in second step, h1 is not equal, h1 x bar is not equal to mu, then it is two tail test. In case of two tail test, if modulus calculated modulus of z value is less than z alpha, we yes, we accept H naught. Otherwise, I mean greater than Z alpha, we reject H naught. In case of right tail, also same thing. If calculated Z value is greater than Z alpha, we reject H naught. If calculated Z value is less than Z alpha, we accept H naught. In case of left tail, if calculated Z value is greater than Z alpha, we accept H naught. Otherwise, we reject H naught. Opposite to those of two tail and right tail test. So next, so this is the procedure. So first step, we have to set up H naught. Second step, we have to write H naught, H1 based on the given problem. In some problems, it is given directly H1 X bar greater than mu or H1 less than mu. So greater than mu means you have to use right tail test, less than symbol if appears, left tail test, or not equal to symbol appears, then two tail test. So then choose level of significance, generally 5% or 1%, and statistic is to Z is equal to T minus expectation of T by standard of T under H naught. And conclusion, if calculated Z value is less than table Z value, accept, otherwise reject. Or in case of negative left tail test, it will be different. If calculated Z value is greater than table Z value, we accept, otherwise we reject. So next, test of significance for large samples. We know that for n greater than 30, the number are very approximately. So if x follows n mu comma sigma, so z is equal to x bar minus mu by sigma. So t minus exponent of t by variance of t. T will be x rasanante. So t minus exponent of t by sigma. Instead of t, I write x bar. Then x bar minus exponent of x bar is mu. Variance of x bar is sigma. So like this, z is equal to x bar minus mu. So the maximum area lies in between, from normal curve, maximum area is lies in between -3 to +3. This can be written as probability of modulus of z greater than 3, 1 minus modulus of less than or equal to 3, 1 minus point, so 0.007 left on the tails, 0.0007. The maximum area lies in between 0.99, 99.73, not 0.9973. So these are not necessary. Now, test of significance of single mean, large sample test. This is the first test. Here we have to, in this unit, here in this last topics, we have to cover 4 tests. Number 1 is test of significance of single mean, test of significance of difference of two means, test of significance of the single proportion, and test of significance of difference of two proportions. These are the 4 tests you have to study. You will get the uh, problems from these 4 tests for the examination point of view. Suppose now we are discussing hypothesis concerning one mean, means a single mean. Suppose x1, x2, and so on, xn be a sample of size n drawn from a normal population whose mean is mu and variance is sigma square. Let x bar denote the sample mean. The test to test the significant difference between sample mean and the population mean, that is x bar and mu, we state the null hypothesis as H naught. There is no significant difference between. I already told you in H naught, this word will appear. There is no difference. In common, we will take, there is no difference. We assume like that. There is no difference between. We are assuming like that. So likewise here also, there is no significant difference between the sample mean and population mean. Okay, that meaning that the meaning of that is the sample has been drawn from the population with mean whose mean is mu and variance is sigma square. So that is the meaning. So you write H naught like this. There is no significant difference between the sample mean and population mean. That we can write symbolically H naught x bar is equal to H naught x bar is equal to mu. So here to test the H naught, we have used the following standard normal test statistic. Z is equal to x bar minus mu. Standard of x bar is sigma by root n. Sigma by root n. So now you compare the calculated Z value with the table value at 5% or 1%. If calculated Z value is less than table value, we accept H naught. Otherwise, reject H naught. Otherwise means if calculated Z value is greater than or equal to table value, we reject H naught. So this is the procedure that we are going to apply in the this first model, that is the test of significance single mu. So here H naught, remember H naught x bar is equal to mu, and H1 x bar is not equal to mu, two-tailed test, and you take Z is equal to x bar minus mu by sigma by root n. If calculated Z value is a modulus, calculated Z value is less than table value, accept H naught, otherwise reject H naught. So this is the way of drawing the conclusion, taking the decision. So this is test of significance of single mu. Now we'll go to problems. So here a random sample of 400 flowers, a random sample of 400 flower stems has an average length of 10 centimeters, full stop. Can this be regarded as a sample from large population with the mean 10.2 centimeters and SD of 2.2 centimeters? So here what has given a random sample of 400, n value is given, 400 stems has an average length of 10 centimeters. So x bar is given, n is given, and population mean mu is 10.2, population SD sigma is 2.25. So first you write what has given, n is equal to 400, x bar is 10, mu is 10.2, sigma is 2.25. We have to conclude that can this be regarded as a sample from a large population with mean 10.2? So or the sample has been drawn from the normal population with mean. So you have to write H naught like this. You please learn this, how to write H naught based on this sample. ఇక్కడ ఇచ్చింది ఏమంటే, can this be regarded as a sample from large population with the mean 10.2? So here we have to check the sample is drawn from this population whose mean is the 10.2 and SD is 2.25. That is the question here. You have to check the sample for 400, these values are taken from this population whose mean is 10.2 and SD is 2.25. That we have to check. That is why here the sample has been drawn from normal population with the mean mu 10.2 centimeters and SD 2.25 centimeters. So symbolically you can write H naught mu is equal to 10.2, mu is equal to 10.2. Then immediately H1 mu is not equal to 10.2 because in this problem it is not given mu greater than 10.2 or mu less than 10.2. Yes, nothing is given, so we'll simply take mu is not equal to 10.2. So it is a two-tailed test. So now we prepared H naught, where H naught is mu is equal to 10.2. The meaning of this is the sample has been drawn from the normal population with the mean mu 10.2 and SD 2.25. This sentence can be symbolically written as like this: H naught mu is equal to 10.2, and automatically next step you have to write H1. H1 is mu is not equal to 10.2. It is a two-tailed test. Next, since n is greater than 30, that is 400, so we have to apply large sample test. Under large sample test we use Z test. So under H naught, Z is equal to calculated Z is equal to x bar minus mu by sigma by root n. That is 10 minus 10.2 divided by this. We'll get minus 1 point. So in case of two-tailed test, I already told you, take modulus. If negative value will get, if negative value will get, otherwise not necessary. If negative value will get, you take modulus, calculated modulus of Z is 1.77. So this is another important point you have to remember. So if suppose in two-tailed test, calculated Z value will get minus, you take modulus, so that it becomes positive 1.77. So critical value of Z at 0.5% LOS is 1.96. So you know, in case of two-tailed test, already I told you Z alpha by 2. So here I given you. Yes, in case of two-tailed test, alpha 5%, alpha by Z alpha by 2 is 0.025. Not here. This is 0.025, and this is 475, and Z alpha by 2 value is 1.96. So that you are using here. So here also given Z alpha by 2 at 5% is 1.96. From this table, we can remember that. So here, in this case, this is very simple. So Z alpha by 2, because it is two-tailed, you have to take Z alpha by 2 is 1.96 plus 1.96. So this is 1.77, this is 1.96. So since calculated modulus of Z is less than, so 1.77 is less than 1.96. So since calculated modulus of Z is less than table value or critical Z value at 5% Z alpha by 2, we accept H naught. So this is the decision. Based on this statement, this is decision. Since calculated Z value 1.77 is less than table value 1.96, so at 5% alpha, we accept H naught. So accept H naught means what you are assuming H naught, the sample has been drawn from the normal population with mean mu is 10.2 and SD is 2. Sigma is equal to 2.25. So that is the conclusion you have to write here. Therefore, the sample has been drawn from a normal population with a mean of 10.2 centimeters and SD of 2.25 centimeters. So this is the procedure of solving the problem. So first, you have to write what has given values. Here n value is given, n is 400, so n is greater than 30. So it is a large sample test you have to apply here. And sample mean is given, population mean sigma. Based on these given observations, we have to memorize that you have to use a test of significance of single mean. Oh, that is that idea we have to get. So that test you have to apply here because x bar, mu, sigma, these values are given and n is 400. So n greater than 30. So large sample test. Then immediately you write H naught. The sample has been drawn from the normal population with the mean mu and like that. Or H naught is mu is equal to. Then write H1. H1 is two-tailed, not equal to is the two-tailed. Then go for calculated Z. Since you are getting minus value here, you take modulus. So then table value at about 5% critical value or table value both are same. 5% LOS it is 1.96. This is from table. So since the calculated modulus of Z is 1.77 is less than 1.96, we accept H naught. Accept H naught means whatever you are assuming under H naught, the sample has been drawn from the normal population with the mean mu 10.2 centimeters and SD sigma 2.5. So this is the way of writing conclusion. So this is the way of various steps involved in solving a problem. Okay. So the remaining we will discuss next class. Okay, ma. Thank you. Have a nice day.